next and the last category of differential equations that we are going to study is the following: is the second order differential equations that are linear and with constant coefficients. So let me tell you what this means. So a second order, and I basically copy a second order linear and differential equation with constant coefficients is an equation of the following form. So it is a second order and normal form. So here you simply have y second plus ay prime plus by equals f of t with a be real. Okay? So, real numbers, notice that these are the two coefficients, a and b, these are the coefficients. Remember that in the previous case here, we had a linear equation. This is a linear equation, and the coefficient here was a, but a, coefficient in the sense that it multiplies the unknown y, or the derivative and so on, but a was a function, so a function that was playing the role of a coefficient. This time, coefficients are not functions, they are numbers, and numbers can be considered as constant functions. So, constant means they are real numbers. Then there is another important term here. This is called the forcing term. Or external force, or for short, I will often use this term, source. So you see there is a physical root behind this term. Forcing term, it means that here you are considering a physical system. You will see that this is typically a harmonic oscillator. A physical system that is going by itself, self-consistently with this equation, but then you act on it with this term which is known. It is not an unknown. So you call it forcing term, or it is an external force when you push, for instance, periodically a harmonic oscillator or a pendulum. And source means that something external that produces an action on your system, okay? This is just a terminological remark, but it is important because words are important, like a very well-known Italian movie director used to say. So, and let me give you another definition here. If f of t is equal to 0, so there is no source, the equation 1, this is 1, is called homogeneous. And another related definition is the following. Given the equation 1, the other equation with the same left-hand side, so y second plus ay prime plus by, but with no forcing term, so it is a homogeneous equation, but with the same left-hand side, with the same a and b here. This is called the homogeneous equation associated to 1. Okay. And so this will be very important, because in order to find the solution, we will see that in order to find the solutions to this equation, the equation 1 non-homogeneous equation, it will be extremely useful to pass through the solutions of this. Okay, so let us go with theorem 1. We're talking about solutions, so the theorem 1 is a so-called structural theorem, because it gives you the structure of the integral, of the general integral, which means the set of all solutions. Do you remember? They are infinitely many. But this set, since the equation is linear, this set is quite particular. So, this equation is 2. So given the two functions y1 of t and y2 of t that are solutions to 2, and suppose that they are linearly independent. What does it mean? This is a very important notion that will be useful in the course of geometry. The whole course of geometry or linear algebra is based on this notion, okay? So namely, this means that if C1 y1 of t plus C2 y2 of t is equal to 0, with C1 and C2 real numbers equal to 0 for every t, then C1 is equal to C2 is equal to 0. So linearly independent means that the only way to combine the two solutions just by multiplication by numbers and sums, the only way to combine these two solutions in such a way that the result is 0 is to choose C1 and C2 equal to 0. And let me give you a statement. The only vanishing linear combination is exactly this. Of y1 and y2 is the trivial one. Trivial because the two coefficients that I have to use are both trivial, are both 0. On the other way around, you see there are these two functions, y1 of t, y2 of t. Okay? I want to combine them linearly, namely by these structures, so associating to every function a coefficient and then summing the two results. So it is clear that if the two coefficients are equal to 0, then the combination is equal to 0. What is not trivial a priori is the reverse. If the combination is equal to 0, then the two coefficients are equal to 0. This is the definition on linear independence. We can discuss it a bit. It is easy, it's not difficult, but it is very deep. You will have to deal a lot with this idea. Okay? So, and this is said to be linearly independent. Now, theorem 1, given y1 and y2, solution to 2, supposing that they are linearly independent, namely this happens, then the general integral of 2 is given by y gen of the homogeneous equation of t is equal to a linear combination of these two, y1 and y2, for every c1, c2 in R. Okay? This is extremely important, so we have to comment a bit on that. Comments. Sorry, here. Of a homogeneous equation. Comments. So previous theorem, theorem 1, states that the general integral of what? Of a second order linear homogeneous ODE is a linear combination is the set of all possible linear combinations of any linearly independent couple of solutions okay. This is theorem 1. The general integral of a second order linear homogeneous OD is the set, the general integral is the set of all possible linear combination and linearly independent couple of solutions. This was the first comment. Let me give you the second comment. Notice that if y1 and y2 are two solutions to the equation 2, which is homogeneous, then for every C1, C2 in R, the function y of t is equal C1 y1 of t plus C2 y2 of t is a solution. 2, 2, 2, 2 to 2. Wonderful. Indeed, consider y second plus a y prime plus b y. This is equal to c1 y1 second plus c2 y2 second plus a c1 y1 prime plus c2 y2 prime plus b c1 y1 plus c2 y2, and this is equal to c1. So gather all terms with c1. We have y second a y prime plus b y1. So here's y second y1 second plus a y1 prime plus b y1 plus c2 y2 second plus a y2 prime plus b y2. But whatever is in the brackets, for instance this is equal to 0 because y1 is a solution. In the same way, this 2 is equal to 0, since y2 is a solution. Solution to what? To the equation 2. So everything here at the end amounts to 0, then y is a solution to 2. So here we have a very powerful method in order to produce infinitely many solutions. So you take two functions, provide that they are linearly independent, and then just combine them. And so you have infinitely many solutions. The third So here we notice that every linear combination of solutions is a solution, and the theorem says that there are no other solutions. This theorem establishes that all solutions to 2, so the general integral, can be obtained in this way. here you see how powerful this method is, how powerful this theorem is. Hmm? And the last comment is the following. Notice that in black, I want to write it in black. The general integral of 2 has 2 arbitrary constant. This is not really surprising because 2 is a second order differential equation. So we need the two constants like in the example of the falling object. And the fifth comment is the following. I want to give you some example of linearly independent functions. So it is very easy. Here, for instance, you have e to the x, e to the minus x. Indeed, consider combination c1 e to the x plus c2 e to the minus x equal to 0 for every x or for every t. So for instance, for x equal to 0, you have c1 plus c2 equal to 0. And then differentiating, for instance, you have c1 e to the x minus c2 e to the minus x equal to 0. And so evaluating at x equal to 0, you have c1 minus c2 is equal to 0. So here you have a system, c1 plus c2 equal to 0, c1 minus c2 equal to 0. The system of the yellow equation made of the yellow equations implies can be solved only by c1 equal to c2 equal to 0, or sine of x cosine of x, e to the x e to 3x, and so on. So general rule you have to apply. A couple of functions f1, f2 forms a set of linearly independent functions if and only if, first, neither f1 nor f2 are identically zero, so they are not trivial. If one of them is trivial, then this set is not made of linearly independent function. Second, f1 is not equal to f2, possibly multiplied by a constant. They are not factor one of the another. They are not proportional, multiplied by a real constant. So it is very easy. Okay? When you have two different functions and one is not the other multiplied by a real constant, then they are linearly independent, provided that they are not zero. And but attention, so warning, the notion, so the rule for more than two, for instance, 3, to be linearly independent is more complicated. Now I'm getting to abstract, so you fear probably me when I'm getting to abstract, so exercise. Find the general integral of the equation, homogeneous equation, y second minus 3y prime plus 2y is equal to 0. Okay? Now we have to find, one aim at finding two linearly independent solutions. Now here you have to try, but you can have an idea for a linear homogeneous ODE, but this time first order. One has a Malthus equation. So y prime is equal to ay. One has that the solution is given by the exponential, the general integral, is y gen is equal to c e to the a t. So let's try for what? For the exponential here too. So consider y equal to e to the lambda t, and so you have that y second minus 3y prime plus 2y is equal to what? When you differentiate 2 times e to the lambda t, you end up with lambda second e to the lambda t minus 3 lambda e to the lambda t plus 2 e to the lambda t equal to e to the lambda t lambda squared minus 3 lambda plus 2 is equal to 0. Then since lambda squared minus 3 lambda plus 2 must be equal to 0, as the exponential is never equal to 0, then we have this is equal to lambda minus 2 lambda minus 1, then lambda equal to 1 and 2 are the solutions to the algebraic equation. And so y1 equal to e to the power t, y2 equal to e to the power 2t are a couple of linearly independent solutions. Then ygen of the homogeneous of t is nothing but e to the t here, e to the 2t, and then provide the linear combination. Here c1 plus c2 for every c1, c2 in R. This is the general integral. Okay, so it is extremely simple. And they are linearly independent. They're linearly independent because they are not the same function multiplied by a constant. Oh, by the way, notice that there is a correspondence here from this equation, the differential equation, and this other equation. Here the correspondence is that when you have the second derivative, you put lambda square. When you have the first derivative, you put lambda and so on. And the second one is called the associate algebraic equation to asterisk here. Okay. Now another theorem. Now we go to the general integral . This is also called the structural theorem, and this is the structure of the general integral of 1, which is not homogeneous. And so the general integral is with the f. Okay, equation 1 is this. So now the theorem says that the general integral of the equation 1 is given by ygen of t is equal to the general integral of the associated homogeneous equation with 0 instead of the source plus yp of t. And what are this symbol? Where y gen hom is the general integral of the homogeneous equation to associated to 1 second yp is a particular integral of 1. Remember what I told you in the last video. Particular integral means a solution, an integral, which has nothing of particular, a specific solution. Example. Take the same homogeneous part as before. So y second minus 3y prime plus 2y, but now it's equal to 1. Okay? The associated homogeneous equation has already been discussed. And as a particular integral, this is easy, because since the source is constant, we can suppose, you can try yp equal to constant, and then you have y second, which is equal to 0, minus 3y prime, which is equal to 0, plus 2yp. This is equal to 2yp, is equal to 1. So yp is equal to 1/2. This is a particular integral. Therefore, the general integral is the following. Y gen of t is equal to c1 e to the power t plus c2 e to the power 2t plus 1/2. And this is the end. Okay, and now we stop.